Learn like a pro.
All right, got a chemistry test coming up? I bet you know the feeling. You're staring at your notes, and the words oxidation and reduction are just kind of swimming around in your head. Well, take a deep breath. We're going to make this all click. And hey, if you're finding this topic seriously confusing, you are definitely not alone. I mean, it's one of the biggest hurdles for chemistry students pretty much everywhere. But the good news? It's really not as complicated as it looks. So, let's just forget all that confusion. Seriously. In the next 5 minutes, we're going to build your complete toolkit. We're not just going to memorize rules, we're going to actually map out the architecture of how these electrons move. Okay, so let's get right to the source of the problem. You know, the reason this whole redox thing can feel so tricky is that you're often taught like 4 different definitions all at once. It makes it seem like 4 separate topics, but they're not. They're just 4 faces of one single core idea. You've probably seen a table like this, right? The 4 common ways to define this stuff. So oxidation could be gaining oxygen, like when iron rusts, or it could be losing hydrogen, or losing electrons, or an increase in oxidation state. And reduction is just the opposite of all that. Yeah, it's a lot to juggle. But what if I told you that you don't actually need to memorize all 4 pairs? What if there was one of them, just one, that's like a master key? A key that unlocks and explains all the others every single time. Well, that master key is the concept of oxidation states. This right here, this is your universal tool. Seriously, if you can master this one idea, you can solve any redox problem that your test throws at you. So what even is an oxidation state? Okay, think of it like a tracking number for electrons. It's this sort of hypothetical charge we assign to an atom just so we can keep a record of where its electrons are, or at least where they're most likely hanging out. All right, this pyramid you see here, this is going to be your best friend for the test. It's called the periodic hierarchy, and it basically gives you the order of operations for assigning those charges. And here's the most important part. You always start at the bottom and work your way up. Always. So let's break it down. Level 1, the base. Any element all by itself is 0. Super easy, right? Then, level 2. These are what I call the rigid anchors. Think group 1 and 2 metals, aluminum, and group 17 nonmetals. They have these fixed, super reliable charges. And finally, level 3, the shifters, hydrogen and oxygen. They have their general rules, but you gotta watch out for exceptions. Like oxygen and peroxide, it's a -1 instead of its usual -2. And that is a classic test question, by the way, because it totally checks if you're using the hierarchy right. Okay, this slide right here, this solves the biggest mental hurdle with this whole topic. Just remember, electrons are negative. So if you lose a negative thing, your overall charge actually goes up, and that's oxidation. It makes sense, right? And if you gain a negative electron, your charge goes down. That's reduction. So moving right on this number line is oxidation, moving left is reduction. Simple. All right, now that we've got our hierarchy and our golden rule, let's actually put them to work. It's time to get into the practical side of things, the mechanics of the math. And trust me, it's way simpler than you think. Okay, rule 1 of the mathing. For any neutral molecule, the total of all the oxidation states has to add up to 0. They got to balance out perfectly. So take SO2. We know from our pyramid that oxygen is a -2, right? And we've got 2 of them, so that's a total of -4. For the whole thing to equal 0, what does that one sulfur atom have to be? Yep, it has to be +4. See, it's just simple math. And what's great is that this system scales up super easily. Even when something that looks more complex like CaSO4, the rule still works. We just use our hierarchy to find our anchors first. Okay, calcium is in group 2, so it's a +2. Oxygen is a -2, and we have 4 of them, so that's -8. So we have a +2 and a -8. That means we need a +6 from that sulfur to get everything back to 0. But what happens when it's not a neutral compound? Well, for ions, you do the exact same thing. You just balance to the ion's total charge instead of 0. Let's look at the sulfate ion, SO4 with a 2- charge. The overall charge is -2. Our 4 oxygens are still -2 each, so that's -8 total. So what plus -8 equals -2? You got it. The sulfur must be +6. Okay, so now you can literally calculate the oxidation state of any atom in any compound, which means we can finally get to the cool part, analyzing full-on chemical reactions and actually tracing the flow of electrons. This right here, this is your blueprint for analyzing any redox reaction. The plan is simple. First, work out the oxidation state for every single atom. Second, and this is important, ignore those big balancing numbers out front when you're calculating the states. And third, find what changed from the left side of the arrow to the right. These flow brackets we're going to use, they show us exactly what's happening. If the number goes up, it's oxidized. If it goes down, it's reduced. Let's see this thing in action. So in this reaction, we do the math and find that sulfur in H2S starts out at -2. Then, on the product side, it's just sulfur by itself, so it's 0. It went from -2 up to 0. That's an increase, so the H2S was oxidized. Meanwhile, you've got nitrogen in HNO3 starting at +5 and ends up at +2 in the NO. Its number went down, so the HNO3 was reduced. See, it's really just about connecting the dots. Now, this next example really shows you the power of that hierarchy pyramid. Here, we've got hydrogen peroxide, H2O2. Remember, our hierarchy told us this is one of those special exceptions where oxygen is -1. And look, we can see it goes from -1 on the left side to -2 in the water on the right. Its state decreased, so the H2O2 was reduced. This method catches those tricky cases for you every single time. And here you go. This is the exact sentence that will get you full marks on your exam. Don't just write, "it was oxidized." You want to use this formula. State the substance, say if it was oxidized or reduced, point out the specific atom that changed, and then state exactly how its oxidation state changed, from what number to what number. It's clear, it's precise, and it screams, I know what I'm talking about. All right, let's put this all together. We've gone through the why, the rules, and how to actually use them. So now it's time for a final review to lock it all in.
This right here, this is the slide to screenshot. Seriously. This is your entire toolkit on one single page. You've got the golden rule number line, the hierarchy pyramid, the math for molecules and ions, and the flow brackets for finding the evidence. Just track the numbers, find the flow, you've totally got this.
And finally, let's remember why this stuff even matters, This isn't just some abstract topic for a test. This electron transfer, it's literally the engine of life. It's how a battery in your phone works. It's how plants during photosynthesis reduce carbon to build the glucose that stores the sun's energy. And then, in respiration, your body turns around and oxidizes that glucose to release that energy so you can do everything. So you see, you haven't just learned how to ace a chemistry question. You've learned how to read the fundamental chemical transactions that power our entire planet. You can now track the very flow of electrons that powers life itself. So the only question is, what will you analyze next?